How 19th century machines worked without a modern power source. When you enter an industrial museum displaying 19th century machinery, the immediate impression is one of technical impossibility. Mechanical looms weighing several tons operating simultaneously, forging hammers moving with rhythmic precision, giant saws continuously cutting wood, hydraulic pumps lifting thousands of liters of water, and industrial presses applying hundreds of tons of force, all functioning for hours on end. Without electric motors, diesel generators, or gas turbines. An information plaque vaguely mentions that the machines were powered by steam or water, but this superficial explanation fails to capture the extraordinary ingenuity of the systems that allowed the Industrial Revolution to happen decades before electricity was available. A fundamental question that historians often fail to adequately answer is how exactly energy was generated, transmitted, and distributed through complex industrial facilities using only fundamental mechanical and physical principles. The answer reveals technical sophistication that rivals modern systems in creativity, if not efficiency. Begin by visualizing a typical 1850s textile factory in Lancashire, England. A five-story building constructed specifically to house hundreds of mechanical looms, each requiring continuous motive power to operate. There were no electrical outlets, no individual motors, no batteries or fuel cells. Instead, all power came from a single centralized source transmitted mechanically throughout the entire structure via an ingenious system called a line shaft with drive belts. At the heart of the installation was a massive steam engine, often occupying a dedicated room in the basement or a separate annex. This machine, developed through decades of refinement from early designs by Thomas Newcomen in the early 1700s to efficient designs by James Watt in the late 1700s, converted thermal energy from burning coal into rotational mechanical motion. Boiler water heated water to pressurized steam that expanded in a cylinder, pushing a piston connected to a connecting rod that rotated a massive flywheel. This flywheel, often weighing several tons and measuring 3 to 6 meters in diameter, stored kinetic energy through angular momentum, smoothing pulses of alternating piston force into steady, continuous rotation. From the steering wheel, power was transmitted to the main shaft, a wrought iron or steel beam that ran the entire length of the building, often 50 to 100 meters. This shaft rotated continuously in lubricated bearings, mounted at regular intervals along its length. Typical rotational speed was 100 to 200 revolutions per minute, balancing the need for torque with the mechanical limitations of materials. From the main shaft, power was distributed vertically through secondary shafts that ran to each floor using bevel gears or pulleys. Each floor then had its own longitudinal shaft from which individual machines drew power via leather belts. The system seemed simple in principle, but required precise engineering to function efficiently. Shaft alignment needed to be perfect to avoid destructive vibration. Bearings required constant lubrication and meticulous maintenance. Leather belts needed exact tension. Too loose and they slipped, wasting energy. Too tight and caused excessive wear on pulleys and bearings. The speeds of different machines were controlled by pulley sizes. The diameter ratio determined speed reduction or multiplication. The operator could engage or disengage an individual machine by moving a driven pulley belt to a free pulley rotating side by side, allowing control without stopping the entire shaft. The efficiency of this system was surprisingly low by modern standards. Energy loss through friction in bearings, belt slippage, shaft bending, and air resistance was substantial. Estimates suggest that only 30 to 40% of the energy generated in a steam engine reached operational machines, the rest being dissipated as heat and sound. But in a time when the alternative was manual labor or animal power, even 30% efficiency represented a revolutionary multiplication of productive capacity. It is critical to understand that this system was not invented suddenly, but evolved gradually through decades of experimentation and refinement. Early factories used water wheels as a power source, a technology that had existed for centuries but was applied on a new industrial scale. A river or canal was diverted to turn a large wheel, often 10 to 15 meters in diameter, which then drove shafts through gears. A limitation was the need to locate the factory near a water source with adequate flow and drop. The steam engine freed industrialization from this geographical restriction, allowing factories to be built wherever there was coal and labor, not necessarily running water. If you're fascinated by the ingenuity of 19th century engineers who created complex mechanical systems using only fundamental physical principles, show your interest by liking this video now. Subscribe to the channel to explore more historical technologies based on documented facts. Turn on notifications so you don't miss investigations into engineering that transformed the world without technologies we consider essential today. And if you want to support in-depth research into real historical industrial technologies, click the Hypar button below. Your support allows us to continue bringing you content grounded in primary evidence and authentic technical documentation. We will examine specific systems in technical detail. Hydraulic systems, prior to electricity, for power transmission. Even before steam engines became dominant, water wheels represented the most sophisticated technology for transmitting power on an industrial scale. Modern understanding often underestimates the complexity of 19th century hydraulic systems, which were the culmination of centuries of development. A typical water wheel in an industrial setting was not a primitive structure, but a precisely engineered machine. Three main types existed, each optimized for specific conditions. The overshot wheel had water arriving from above, filling buckets that then descended by the weight of the water, offering 60 to 80% efficiency under ideal conditions. The breast wheel had water arriving halfway, combining momentum and weight. The undershot wheel had water flowing from below, pushing paddles, less efficient at 20 to 30%, but functional where head was limited. Dimensions were impressive. A large water wheel in an operating mill or factory could be 15 to 20 meters in diameter and 3 to 5 meters wide, constructed of oak wood, reinforced with wrought iron or entirely of cast iron in more recent installations. A water supply canal or aqueduct brought water from a reservoir or diverted river, often requiring substantial civil engineering works including dams, sluice gates, and canals kilometers long. A control system allowed for the regulation of water flow through adjustable sluice gates, changing the speed and torque of the wheel as work demands varied. During periods of high demand, the sluice gate opened completely, allowing maximum flow. During periods of low demand, flow was restricted, conserving the reservoir. In winter, when freezing came threatened, the system required constant monitoring and sometimes heating of the canal to prevent ice formation that would block operation. Power transmission from the water wheel to machinery followed principles similar to steam-powered systems. The central wheel shaft, often made of solid oak 40 to 60 centimeters in diameter, reinforced with iron, connected to gears that reduced the high wheel speed to a speed appropriate for the main factory shaft. Reduction was necessary because a large water wheel could only rotate at 5 to 15 revolutions per minute, while textile machinery operated efficiently at 100 to 200 revolutions per minute. Gears were often apple wood or oak teeth inserted into a cast iron wheel, a combination that offered durability and the ability to replace individual teeth when worn without replacing the entire wheel. Lubrication was animal fat or vegetable oil applied regularly by a dedicated worker. The advantage of hydraulic power was essentially zero operating cost after initial infrastructure investment. Water flowed continuously without the need for fuel. The disadvantage was dependence on natural conditions. Summer drought reduced flow, decreasing available energy. Flooding could damage structures. Winter freezing could stop operation completely. These limitations forced the development of hybrid systems where a water wheel provided primary energy, but a supplementary steam engine was available for periods of low flow. Geographic location was critical. Mills required locations where rivers had sufficient drop or where a dam could create a high reservoir. The topography of New England in the United States and the Pennines in England was ideal, resulting in a concentration of textile mills in these specific regions during early industrialization. Stationary steam engines and applied thermodynamic principles. The steam engine represented a transformative advance because it freed industrial production from the geographical constraints of hydraulic power, but the actual operation of 19th century steam engines involved sophistication that goes beyond the usual simplified explanations. A typical 1860s factory steam engine was a complex system of integrated components. It began with a boiler, often a horizontal cylindrical type, constructed of riveted iron plates, containing water heated by a furnace burning coal. Steam pressure was controlled between 40 and 100 pounds per square inch, sufficient to generate power, without exceeding the safety limits of available materials. Boiler explosions were a real risk that motivated the development of safety valves, pressure gauges, and eventually, government regulations on inspection and operation. High-pressure steam flowed through piping to a cylinder where it expanded, pushing a piston. Linear piston motion was converted into rotation through a connecting rod and crank mechanism. Critically, after pushing the piston in one direction, used steam needed to be evacuated, and the piston returned to the start of the cycle. This was achieved through a sliding valve that alternated between the intake of fresh steam and the exhaust of spent steam. precisely synchronized with the piston position. A centrifugal governor, a brilliant invention of James Watt, automatically controlled the machine's speed. Heavy spheres mounted on articulated arms rotated, driven by the machine. As speed increased, centrifugal force caused the spheres to rise, a movement that, through a system of levers, partially closed the steam valve, reducing pressure and consequently speed. If speed decreased, the spheres descended, opening the valve. This automatic mechanical feedback maintained remarkably constant speed without human intervention, allowing for stable operation of connected machinery. The thermodynamic efficiency of 19th century steam engines was low, typically 5 to 10% in early designs, improving to 15 to 20% in later compound designs where steam expanded sequentially through multiple cylinders of increasing diameters. Most of the energy contained in coal was lost as heat in the exhaust gases and radiation from hot surfaces. But compared to contemporary alternatives, animal power or human labor with even lower efficiencies considering feed and maintenance costs, the steam engine was a revolutionary advancement. The size of the installations was impressive. A large factory steam engine could have a cylinder 1 meter in diameter with a stroke of 2 meters, consuming tons of coal per hour and producing 100 to 200 horsepower. The flywheel weighed 10 to 20 tons, its enormous mass serving to smooth pulses of force and provide the torque that carried the machine through dead center where the piston changed direction. The engine room was the domain of specialized engineers who monitored operation, adjusted controls, lubricated bearings, and made repairs. Knowledge was often transmitted through practical learning, not formal education, creating a class of highly skilled technical workers. Maintenance was intensive. Bearings required constant lubrication with mineral oil or grease. Gaskets around piston rods needed regular replacement to prevent steam leaks. Boilers required periodic cleaning to remove mineral deposits that reduced heat transfer efficiency. Regular inspection of rivets and plates was essential to prevent catastrophic failures. Mechanical transmission via shafts and leather belts. The line shaft system, which distributed power from a central source to individual machines throughout a factory, represents a triumph of mechanical engineering that deserves detailed examination. The main shaft was typically solid wrought iron, 15 to 25 centimeters in diameter, and could exceed 50 meters in length in large installations. This shaft was not a continuous piece, but sections joined by riveted flanged couplings, allowing for the installation and replacement of damaged sections without disassembling the entire system. Support came from bearings spaced every 3 to 5 meters, consisting of a cast iron housing containing a bronze bushing where the shaft rotated. Bronze was chosen because it has low friction compared to steel and is wear resistant. Lubrication was critical, achieved through a system of oil-soaked felt pads that continuously touch the shaft, or in more advanced installations, a ring lubrication system where a metal ring suspended from the shaft rotated through an oil reservoir at the base of the bearing, carrying oil to the contact surface. Each bearing required daily oil level checks and periodic cleaning of accumulated dirt and metallic residue. Transmission belts connecting line shafts to individual machines were works of craftsmanship in themselves. Constructed of multiple layers of tanned leather stitched or riveted together, belts could be 10 to 60 centimeters wide and several meters long depending on the distance between pulleys. Thickness was typically 5 to 15 millimeters. Proper tension was essential, achieved through tensioning pulleys or machine position adjustment. A belt that was too loose would slip, wasting energy and generating frictional heat. A belt that was too tight would overload bearings and cause premature wear. Belt care was the specific responsibility of the worker. Leather needed regular treatment with grease or oil to maintain flexibility and prevent drying out, which led to cracking. Splices where belt ends were joined were potential failure points requiring frequent inspection. When a belt broke during operation, an event that could be dangerous if the belt whipped, established procedure required stopping the shaft, removing the damaged belt, and installing a spare belt or repairing the splice before restarting. Pulleys mounted on a shaft were cast iron discs with slightly arched faces to keep the belt centered. Through a crowning effect, diameters varied according to the desired speed of the connected machine. Machines requiring high speed used a small pulley on the shaft and a large pulley on the machine, creating speed multiplication. Machines requiring high torque used the opposite configuration. Calculating pulley ratios was basic mathematics, but application required consideration of practical factors such as belt slippage and transmission efficiency. An ingenious system allowed engaging or disengaging individual machines without stopping the main shaft. Two pulleys were mounted side by side on the shaft, one fixed and one free to rotate independently. The belt normally ran on the free pulley when the machine was stopped. To start the machine, the operator used a rod or lever mechanism to laterally move the belt from the free pulley to the fixed pulley, engaging the transmission. Skill was required to do this smoothly without damaging the belt or causing a sudden start that could brake components. The sound of a factory in operation was a characteristic cacophony of whistling belts, vibrating shafts, clicking gears, and humming machinery. The rhythm was constant and hypnotic, with workers developing an ability to detect abnormalities by subtle changes in sound that indicated emerging problems before complete failure occurred. Hand-cut gears and surprisingly precise tolerances, the manufacture of mechanical components for 19th century power transmission systems, represents an often overlooked but absolutely crucial aspect. Gears that transferred motion between shafts needed to be precisely cut to operate smoothly and efficiently, but this was accomplished without modern CNC machines, laser cutting, or computers. Instead, skilled craftsmen used techniques developed through centuries of practice. A large gear for speed reduction between a water wheel and main shaft could be 2 to 3 meters in diameter with 60 to 120 teeth. The process began with molding the gear body from cast iron using a wooden pattern. After cooling, the raw disc was mounted on a large lathe where the face was machined flat and the central hole was enlarged to receive the shaft. Dividing the circle into equal spacings for teeth was done using a dividing plate, an ingenious device with a series of holes in concentric circles that allowed precise rotation of the part in exact increments. For an 80-tooth gear, the craftsman would use a circle with 80 holes, advancing an indexing pin 1 hole for each tooth. Individual tooth profile cutting was done with a specially shaped cutting tool mounted on a machine called a gear cutter. Early versions were manually operated. Later versions were motorized but still required specialized setup and supervision. The cutting tool had a profile complementary to the tooth spacing, a shape that needed to be geometrically correct to ensure that the teeth of two mating gears meshed smoothly without interference or excessive backlash. The process was tedious, each tooth taking several minutes to cut, and a large gear requiring days of work to complete. Tolerances achieved were surprisingly tight by pre-industrial standards. A skilled craftsman could produce gears where variation in tooth spacing was less than half a millimeter along the entire circumference of a 3-meter gear. This precision was verified using gauges and reference standards, often made of bronze because the material was more dimensionally stable than iron. For applications requiring wooden gears, such as some water wheels, the process was different, but equally skilled. Teeth were separate pieces of hardwood such as apple or oak, cut into precise shapes and inserted into rim-cut sockets. The advantage was that individual teeth could be replaced when worn without discarding the entire wheel. The disadvantage was that wood changed dimensions with humidity, requiring seasonal adjustments. Bearings supporting. Rotating shafts also demanded precision. Bronze bushings needed to be enlarged to an exact diameter, leaving enough clearance for a lubricating oil film, but not so much as to allow excessive lateral movement that would cause vibration. Typical clearance was 2 to 5/10 of a millimeter for a 20-centimeter diameter shaft. Enlargement was done with a conical reaming tool, gradually increasing the diameter until the gauge passed through the bushing with light but uniform resistance. The quality of manual workmanship was verified through functional tests. After assembly, the system was operated at low speed, while craftsmen listened for unusual sounds, felt vibrations, and checked for bearing heating. Adjustments were made iteratively until smooth operation was achieved. This empirical process, combined with theoretical knowledge of mechanical principles, allowed the creation of systems that operated reliably for decades with appropriate maintenance. Storage and regulation of kinetic energy through massive flywheels. The flywheel represents a fundamental physical principle applied with particular ingenuity in 19th century machinery. Its basic function is to store kinetic energy during the phase of a cycle where motive force exceeds load, and to release energy during the phase where load exceeds motive force, smoothing fluctuations and providing more uniform operation. In a steam engine, the piston provides force only during part of each revolution when steam is expanding. During the rest of the revolution, the flywheel's momentum carries the system through. Without a flywheel, speed would vary drastically during each cycle, making it impossible to operate machinery requiring uniform motion. The size and mass of the flywheel depended on the application. A small steam engine for a workshop might have a flywheel 1.5 meters in diameter, weighing 500 kilograms. A large machine for a textile factory might have a flywheel 4 to 6 meters in diameter, weighing 15 to 20 tons. Most of the mass was concentrated in the outer rim, because the energy stored in a rotating flywheel is proportional to the mass multiplied by the square of the tangential velocity, and tangential velocity increases with radius. This means that for the same stored energy, a flywheel with mass concentrated far from the center can be lighter than a flywheel with uniformly distributed mass. The construction of a large flywheel was a significant engineering project. Molding a cast iron piece weighing 20 tons required specialized foundry work capable of producing and pouring this quantity of molten metal. Cooling needed to be controlled to prevent internal stresses that would cause cracking. After molding, the flywheel was machined on a large lathe to ensure the outer surface was perfectly circular and balanced. Imbalance in a flywheel rotating at high speed would create centrifugal forces that would cause destructive vibration. Balance was checked by mounting the flywheel on a shaft supported by low friction bearings and allowing it to rotate freely. If it consistently stopped at the same point on the base, it indicated that this point was heavier and required material removal or weight addition on the opposite side. Mounting the flywheel on the shaft was done using a hub with a tapered bore that fit into a corresponding tapered section of the shaft. The fit was very tight, often requiring heating the hub to expand it, allowing it to slide on the shaft. Then upon cooling, it contracted, creating an extremely tight connection. A metal key was inserted into a channel cut partially in the shaft and partially in the hub to prevent relative rotation. Safety was a constant concern, because flywheel failure at high speed was catastrophic. Centrifugal force on a 3-meter flywheel kidney spinning at 100 revolutions per minute was enormous. If material failed, or if the speed exceeded the safety limit, the flywheel could fragment, sending pieces weighing several tons through building walls. Historical accounts describe accidents where flywheel fragments traveled hundreds of meters, causing considerable destruction. This motivated the development of safety designs, where the flywheel was built in separate sections, connected by links that would fail in a controlled manner before the entire kidney fragmented. Automatic speed regulation through a centrifugal governor interacting with the flywheel created a remarkably sophisticated feedback control system. If the load on the machinery suddenly increased, the main shaft speed would begin to decrease. The flywheel released stored energy, maintaining speed temporarily, while the governor detected a drop and opened a steam valve, increasing the steam engine power. The reverse process occurred when the load decreased. This dynamic balance maintained speed within a narrow range, typically plus or minus 5% of nominal speed, without operator intervention, regional adaptations, and creative solutions for local limitations. The implementation of mechanical power systems varied significantly based on local resources, climate, and technical traditions, resulting in fascinating regional adaptations. In mountainous regions of Switzerland and Austria, where rivers had steep drops but variable flow, overshot water wheel systems were extraordinarily refined. Engineers developed optimized bucket shapes that maximized energy capture from falling water while minimizing drag as the empty bucket rose. Some designs incorporated valves in the buckets that automatically opened at the top, draining wastewater and reducing the weight that needed to be lifted. In the plains of the Netherlands, where natural drops were non-existent, but wind was abundant, windmills were adapted for industrial applications beyond milling. Dutch tower mills with adjustable sails generated 20 to 30 horsepower under favorable conditions. The challenge was variability. An ingenious system was developed where multiple mills operated in parallel, connected to a reservoir. During strong winds, mills pumped water into an elevated tank. During calm periods, water from the tank was released through a wheel, providing more constant energy. This primitive but effective storage allowed continuous operation even with an intermittent source. Arid regions of the Mediterranean, where neither water nor wind were reliable, relied on animal power combined with ingenious mechanisms. Horses or oxen walking in circles rotated a vertical shaft connected through gears to a horizontal shaft, powering machinery. Although limited compared to water or steam, the system was simple, reliable, and used local resources. Elaborate gear arrangements allowed the slow movement of animals to be converted into the required rapid rotation. Climate influenced design. Regions with harsh winters, such as New England, required protection against freezing of hydraulic systems. Canals were covered and even heated using exhaust steam. Wheels were designed with extra clearance, allowing operation with some ice formation. In tropical regions, the challenge was accelerated corrosion and deterioration. Wood exposed to moisture had a short lifespan. Solutions included resistant tropical woods such as teak or treatment with tar. Metal parts were galvanized or painted to retard rust. Fuel availability dictated choices. Regions with abundant forests, such as Scandinavia, used wood for boilers. Carbonization techniques, converting wood into charcoal, improved efficiency. Regions with coal deposits, such as Yorkshire or Pennsylvania, naturally favored steam engines. Where neither wood nor coal was abundant, agricultural byproducts like sugarcane bagasse were adapted. The transfer of technical knowledge occurred through the movement of specialized engineers and the publication of treatises. British engineers trained in Manchester were recruited to establish factories in Massachusetts. Detailed designs were published, allowing for replication and adaptation. This exchange accelerated the dissemination of best practices, enabling local innovation. If these revelations about the sophistication of 19th century mechanical engineering are expanding your understanding of how industrialization occurred without technologies we consider essential today, please like this video to support research based on authentic historical technical documentation. Subscribe to the channel to continue exploring past technologies grounded in verifiable facts. Click on the video appearing on the screen to deepen your knowledge of historical industrial engineering. Thank you very much for taking the time to explore the true history of how machines functioned without modern power sources. See you in the next documented technical investigation.